Merhaba herkese. Öncelikle şu okulun düzenlenmesinde başarılı rol oynayan Orhan Hocam'a teşekkür ediyorum. Diğer arkadaşlar Bilal Bey, Oğuzhan Bey, Selahattin Bey, Fatih Bey, herkese teşekkür ederiz. Dersler İngilizceymiş. Ben Türkçe hazırladım notlarım. O yüzden Türkçe'ye bakıp İngilizce'ye çevireceğim. Okay. My talk will be on the theory of special relativity. So this is its abbreviation. First of all, at the beginning, I planned my route in a different manner. So in special relativity, you can talk about this algebraic aspects, geometrical aspects separately. There are many tools here. I will only mention a few of them, literally. And geometrically, you can talk about only on the differential geometric structures residing in the theory of special relativity and the global Lorentzian geometrical parts. So this is related with global analysis on manifolds, okay? Rigorous mathematical sense. Here we have groups. These groups are the Lorentz group, okay, and it's in a linear contraction, Gaussian group. So this is not an easy, okay, because you have from Lorentz group to Gaussian group by taking the vacuum speed of light to infinity. Okay, this is the rule for making contraction. So you can also include the translations embedded in these groups. Then you call these groups respectively inhomogeneous Lorentz group and inhomogeneous Galilean group. Sometimes we call this the Poincare group. Okay, these are very important groups for physicists working on elementary particles in relativity. Okay. But, so these groups have their own Lie algebras. Okay. So one also has to learn the Lie algebras corresponding to these Lie groups. Okay, Lie groups are manifolds, and the group property should be differentiable. So manifolds with group properties, the product of which is differentiable, is called a Lie group. Groups are important in physics. Why? Because many things are based on symmetric principles. Okay? Here, the symmetric principle will be called Galilean principle. If you start with the Galilean principle, you cannot reach to these groups by mere logic, because physics is an empirical science. Okay, we always base our ideas on experiments. So this scheme is logically and mathematically very delicate and should be a subject of another school, a school on only on special relativity, because special relativity is not only Lorentz transformations and the group that they construct when they come together. Okay. So this part is also a great path in the scheme. Here you mainly focus on the causal and chronological structure of the manifold that you are dealing with. For example, it should be a solution of Einstein's field equations. So here there are many techniques from geometry, differential geometry, and I will focus on this aspect of special relativity. So the others, we hope to give lectures on special relativity in another school, maybe. I don't know. Also, here, another path opens itself by representing these groups on specific vector spaces, especially when you want to do relativistic quantum mechanics, which is not an axiomatic, which has not axiomatic foundations in its own sense, but it merely forces us to pass to the quantum theory of fields. So here, the main idea of Wigner is used. He classifies all elementary particles that are the field excitations of the vacuum that you are dealing with, for example, quantum electrodynamics. By doing representation theory on Hilbert spaces, and then it grows into the false spaces of quantum field theory. Okay. So forecasting. special relativity, I'd like to talk about physics in a different manner. So I will use the theory of fiber bundles for constructing an event manifold for classical mechanics in the non-relativistic sense. I mean, I will only use the Galilean covariance. So here I will construct Galilean bundle. So this will be the event manifold classical mechanics, especially particle mechanics. Not the mechanics of fields, okay? It is another subject. So I will give examples from classical particle mechanics. Or I will base my examples on particle mechanics. Then we know that the event space of special relativity is the Minkowski space-time. But before defining it, I will give examples on Maxwell, Lorentz, electrodynamics. So this will be the subject of the lectures of my first day. This will be the subjects of tomorrow. Okay. So the relativity principle, which can be thought as a symmetric principle, the sense of which resides in the effect of groups on sets, okay, which we call G sets. But as I told you before, I will not deal into these topics very deeply. The relativity principle of Galileo Galilei tells us that no one or one cannot detect the uniform rectilinear this uniformity includes rectilinearity, but not vice versa. Motion of a body by performing mechanical experiments. Okay, so Galilei principle. Okay, then comes Newton's laws. First law, second law. Okay. If a body does not experience an external force, it preserves its state of being at rest. So the first law is related to value principle, and it defines the reference frames that we are looking for. Because
it may also be moving with some constant velocity, not just at rest station.
okay, they are equal.
Right, yes.
In my sense, okay. So this principle is very important, and it's related with the Galilean principle, the relativity principle. As I told you before, it divides into two groups in a manner of which G sets are acting, G groups are acting on sets, and it is another subject that I'm not going to talk today. So this gives us the notion of inertial reference frames, okay? Inertial reference frames or inertial reference systems. Okay. The second law is the rate of change with respect to a parameter. It's called the Newtonian time, okay, of momentum of a body is proportional to the force acting on it. This is the second law. And the third law. Two interacting bodies apply mutual forces on each other. That have equal magnitudes and opposite direction. Okay, these are the basic principles of non-relativistic particle mechanics in the classical sense. Okay. When you find an inertial reference frame, so when you put a tick here, these inertial reference frames include inertial observers, and these observers make measurements, so mechanical measurements. But what do you mean by mechanical measurements? We use mass, length, and time measurements. Okay. For example, the electric charge is not included in this set. When you put a tick here, these are also satisfied. And böyle bir şey yapmak istedim. Ha, iyi olur.
Var ya şimdi, şurada da bir
Şeyi idare edeceğim. Olmaz.
haklısınız. Maalesef.
Okay, let's continue. So when you have an inertial frame of reference, and you observe a body, it should be a rigid body or a fluid, maybe a gas system or a liquid system. Okay. Think it as if a rigid body. Okay, you put it here. Its mechanical properties does not change when you transmit it for these observers. Okay. When you direct it in a different manner in space, its mechanical properties does not change. And if the observer make measurements at the time and later on makes the same measurements at a later time, nothing changes. Okay. So according to the inertial observers using these inertial reference frames, space and time are homogeneous. So these are the mechanical properties of space and time with respect to an inertial observer. Mechanical properties of space. And time. Here we can think of space as the vacuum of classical mechanics and space. I also want to say another thing on these postulates, classical mechanics. Note that this first law includes only one body, okay, one particle, let's say. The second law also includes or may be applied to only one body. So these are one body postulates, but the last of these postulates includes two bodies. So this is related to two body problems. Okay? One body, two body. And everybody. Okay? But this is nicht.
Bu tarafı kullanmak imkanı var.
Yok. Sabit. Arkasını göstermeyeceğim bizi. Okay. So, now I can base my arguments on these principles in a different manner while doing some technical work related to the theory of fiber bundles in mathematics or topology. Next time, I was dealing with the electrodynamics of bodies, okay? Huge bodies that are materials. They are called materials today. He was dealing with the polarizability properties of matter in an electromagnetic field. So magnetically polarizable media was his main subject. He started with these things and arrived at the 1905 special relativity paper dealing with the electrodynamics of continuous media. Okay, so when someone asks a question about special relativity to me, I also consider that part of electrodynamics of continuous media. It is still a very rich part of physics. So you can also try to extricate the electrical properties of this polarizable matter in the gravitational field, maybe near a black hole. Okay? What a great problem. So before passing to that subject, I'd like to tell a few words about the absolute space of Newton. So it's isotropic and homogeneous with respect to inertial observation. Okay. It is three-dimensional. A very important number is 3, because when you work on the topology of manifolds, if the dimension of your manifold is 1, 2, or 3, you call it low-dimensional topology. So every topologist may or will be working on that subject in his academic life or her. So we have here Thurston's generalization program. Okay, and Perelman proved the full program, and the Poincare conjecture was a point on that program. And it has a leading geometry. But three-dimensionality in algebraic sense is very important for us. We use the vector calculus of Heaviside Next. Okay. So the PV means we are dealing with Rn and is here free. Okay. And we also know to calculate things on Rn's. Özgür Hoca started mentioning about the geometrical aspect of these manifolds. So we can make here infinite small calculus. It is constructed by Robert Herman and Cavalier. 1630s.
Özgür hocam, sesim geliyor mu?
Evet.
Zoom'dan konuşuyorum. Tahtayı acaba biraz daha bize döndürebilir misiniz diyecektim. Kamera şu an masanın üzerinde. Sanırım bardağın yanında. Evet, çok teşekkür ederim. Çok sağ olun.
Tamam, ben teşekkür ederim çünkü dönüyor ve silemiyorum.
Evet, biz de buradayız. Onu söylemek istedim. Çok teşekkür ederim.
Teşekkür ederim. Okay. And the last state of which was given by Newton. And the 1980s, let's say, because his book was printed in 1686. Okay.
You mean the principia?
Sorry?
Principia.
Principle. Oh, teşekkür ederim. Okay. So, Galileo so in the theory of fiber bundles, if you have a base manifold, here it is the time manifold. It's represented by the real line, and it has given an orientation. This orientation is based on the ordering properties of the real line, okay? Which we denoted by these symbols, okay? Less or greater. So, our total space fibers of which are isomorphic to three-dimensional Euclidean space. Okay. So you have a point, that's an event, okay? You have a projection map. This projection map takes the event and maps it into the real line. So we call it TP. This is the time point. You can also project, but I'm not going to tell you how to project this point onto the model space of the fiber. So this fiber, this is the inverse image of the point TP. So there is a three-dimensional Euclidean space at a time. Okay, so you give coordinates to an event, which I denote by P. You can, in a formal sense, we can say that this is a three-dimensional vector, vector. Okay, so we have coordinatized our bundle. I noted it. It's without G. P. These are the coordinates are in our bundle. This is the time, which was a parameter. Now it is also a parameter, but also a coordinate of an event in this construction. This is also philosophically embedded in the Hamilton-Jacobi formulation of classical methods. Okay. Here, this is the metric space in the functional analysis sense, okay? Not in relativistic sense. In the Einstein's general relativity theory, we have a metric tensor field. But in mathematics, it's just the inner product, okay? So when you have an inner product in functional analysis, you can define a norm, and if you have a norm, you can define a metric, which I call a distance function. So now I'm talking on the distance functions on the base and on the fiber. This is the base space. This is the fiber space. This is the model fiber space. And these are the fiber spaces corresponding to different times. Okay, so every point time you have a three-dimensional Euclidean space, and this arrow tells us that we can formulate a bundle by going through this direction in time and just translating the fiber at this time. Okay. So in this sense, it resembles the Minkowski space-time, but there is no causal structure here. Can one tell me why there is not a causal structure in this scheme? There are no light cones or other things. Because in classical physics, the speed of the signals can be infinite. It is not a finite number as in the case of relativistic particle mechanics. So you have special relativity there. So it's a distance function. Distance function. I should check. So there's a point P. So there's a point. So this would be a number. It can be negative, so it doesn't satisfy the actions of metric actions of functional analysis to metric spaces. But this can be defined as, so you have a norm on real numbers. It is related to the algebraic properties of the real numbers because it is the only one-dimensional real norm division algebra. Okay, there are 4 of them in the niche, and you have an ordering relation. So P is causally before Q if this number is negative. Or if this is positive. So we use the metric on the base to order the events chronologically. So this is if you define the equivalence class of an event, these are the points of Galilean bundle that lie on the same fiber. Okay. Equivalence class of the event P, the set of simultaneous events with K. So one can show that this is an equal relation. So the simultaneous space of P is the fiber that it's lying on. Okay. Okay. When the point Q lies on the same fiber with the event P, this is an equivalence relation. So it is the reflexivity property, symmetry property, and transitivity. So this is your first homework for tomorrow, okay? Then Q and P belongs to the same fiber, since this is also equal to TQ. Then this is R3. Then we can use the Euclidean metric of a fiber, which is given by the Euclidean metric structure of R3 in the functional analysis sense. This means that so I should copy. Okay. Distance at the fiber labeled by time TP. The special parts of the events is given by the norm of this vector. Okay. You can also use the Euclidean metric and inner product in functional analytical sense. This is positive, definite. So we can take its square root and we choose the positive. Okay, positive square. R3 has important structures on it. If you have a chart, a Cartesian chart, it is an adaptive coordinate system on any Rn. Here we are using it on R3. Okay, as Özgür Hoca said, the chart, but it covers all of the manifolds because all Euclidean spaces are flat. Okay, so this Euclidean metric will be denoted by this delta, but this is not the Kronecker Weierstrass delta. It's different because Kronecker delta contains one contravariant index and a covariant index. This is Kronecker Weierstrass symbol. This is the Euclidean components of the metric, Euclidean metric tensor. Okay, these are different because metric and its dual, respectively, lowers and uppers the positions of the indices, as everybody knows in this lecture room. Okay, this is the tensor product. So these are the Cartan derivatives. Okay, the exterior derivative. It is not the ordinary derivative in the one that you are used to deal with, infinitesimal calculus or calculus and internal derivatives. Okay, exterior differential.
You can relate to.
Of Cartan. No, you can relate them when you are defining geometric integration theory on manifolds and mapping those integrals to the model spaces, the Euclidean spaces. But it is not a trivial operation. For example, everybody knows the line element or the square of the line element in this geometry. This is given by dxi dx. These are covariant indices. These are contravariant indices. And according to the convention of Einstein, we are making a sum. Okay. So one index I appears as a covariant index. It's at the below of the delta, and it is the other of which is at the top of X. So we are taking a sum. So we have three-dimensional 1, 4. We give it 1, 1, 2, 2, 3, 2. Okay. Here, these differentials are not Cartman differentials. These are infinitesimal differentials of infinitesimal calculus. These are very different, okay? This is a tensor. This is a measurement, a length measurement. These are related, but they are notionally very different, okay? Okay, let's say I want to coordinatize this bundle by using sections of the bundle, okay? Now, let's do that. Part 3, we have a vector product, okay? This vector product only lives in dimension 3 and dimension 7. And in dimension 3, so it is not associated, so you cannot move the parentheses arbitrarily when you have several products. And it's very rich because when you put infinitesimal calculus and fuse with the algebraic vector product of R3, you reach the vector analysis of Gibson Hellside. Okay. This is very different from the algebra of matrices, algebra of tensors, and algebra of exterior forms, and also from Clifford algebras. This is very unique to dimension 3, because we are not using octonions in physics in general, only in extreme situations. So, for an arbitrary fiber bundle, so you have here your base space, this total space, the model fiber space, the projection map. Okay, this is an arbitrary fiber bundle. You have the base space, maybe we can denote it by M. So there's a notion called the sections of the bundle. Okay, this is the projection map. These are given by curves. Okay. Each curve families of curves. So you can label this prime index. So there are many of these. Curves that foliates A and intersects every fiber once and only once. So I can denote it by as a family of sections. So here, in our case, when we have the Galilean bundle and the model fiber spaces are free. The base manifold is the time manifold. And okay, this is Q. This is P. P. And this is Q. So P and Q are lying on the same curve of this family of sections. So we can here project this curve to the model space and call it lambda. It's a vector in 3 dimensions. So here P is P lambda, Q is PQ lambda. Here Q is, or P is chronologically before the inner Q. Okay. So we can define another equivalence relation P and Q are spatially have the same position. Here P and Q are not so this is also an constellation. Your second homework in the actions. Okay. So to this lambda, I define this curve as S lambda without a vector, because this is a parameter. It is an element of a subset of the real line, because real line has a well-ordering property, as I mentioned before. Okay. So that's your equivalence. This is not temporal one, which I told you before. So they are lying in the image of the same curve, same section. Okay. But lastly, I'd like to tell you how do we select these families in classical mechanics? Okay. Let's try the class of families of sections by identifying these section curves, let's say, by the trajectories of really falling point particles with uniform Newtonian velocities. So this class of curves, this class of families of curves will define the inertial structure of our manifold. And so this foliation defines a coordinatization on the manifold. So these coordinates will be the inertial coordinates in our construction. Okay. So these will be related to the selection of inertial reference frames and the inertial coordinates are defined in this sense. So the relativity principle is imposed by this mathematical construction. And the inertial reference frames, the first law of Newton, is selected in this sense. But this requires the notion of parallelism on this manifold. It's very important. Özgür Hoca and Çetin Hoca will talk much about these connections. The parallelism of the manifold is given by selecting a connection from the space of connections. And this connection defines the covariant derivative. So you can compare any tensorial object at different points on the space-time manifold. Okay, this is the rule, and it's very important. The first technical foundations were given by Christoffel and his student, Julio Levi-Givita. No. Gregorio Ricci-Turbastro and student Julio Levi-Givita. Okay. This notion is found, it's placed by these mathematicians. Okay. I'm going to stop. So this requires the notion of this parallelism is generated by the trajectories of free falling particles. Physically, our motivation is this. In the classical motion of particles in the non-relativistic domain. Okay.
Connections and Christoffel symbols, they are all related to this?
Yeah. But this is non-relativistic physics, okay? But my mathematical construction will be general, okay? One can apply all these things to any manifold. So I'm stopping here. Are there any questions?
There's a connection in the field there is also, like you see in the others, they're also analyzed under the same mathematical framework? Or
There are two types of fields in physics. Two classes, let's say. One class is the Young's theories. Okay. The others are Einstein type theories. When you want to formulate Einstein's general relativity in this manner by using principal bundles, you should use the frame bundles, linear or affine frame bundles, and its model spaces. The fibers are all groups. Okay, they are groups. So when you have groups as fibers, you have Einstein-type physical theories, and when you have vector spaces as model spaces of the fibers, you have Young's theories. But Young's theories can be abelian or non-abelian. Abelian Young's theory is Maxwell theory, which I'm going to talk about later. Any question? Another question? Okay.
So are we somehow defining the bird lines of the particles in the known sense from the general relativity?
Basically, but in this construction, we have a Galilean bundle. So its causal structure is very primitive. You can also define time-like and space-like vectors here, but you cannot define null vectors, so you have no cone structure, no causal structure here in that sense. Causality is defined by this ordering relation here. Okay, but you can decompose a tangent vector that Özgür just started to talk about in this first lecture. So you have a vector. So you have a fiber part and the fiber orthogonal part. If this vector is tangent to a fiber, so it's special. It's a space-like vector. And when it is not tangent, let's say it's direct in this sense, it is time. Okay, this is space-like. If it's tangent to a fiber, it's time-like when it's not tangent. Okay. Teşekkürler. Getirdik. Ne kadar tahta getirirsiniz? Birkaç tane daha olursa sevinirim. Onu kaçmak. Arkadaşlar, hadi koş. Aralarda da konuşabiliriz. Bize soru sorun arkadaşlar. Biz buraya boşuna gelmeyin. Soru sorun. Bizi rahat edin. Bizi sıkıştırın. Bir şeyler öğrenin. 20 dakika mı kaldı? Öyle evet. Tamam. Ben bu için tahtalarla uğraşmak lazım.